get that.
we will talk about the gamma function briefly.
Oh, yeah. Yeah, I'll push this up.
Okay, so the definition of the gamma function is, as you know, a continuous extension of the factorial function. So the definition of gamma of s is, it is the integral from 0 to infinity e to the minus x to the power, we put s minus 1 dx. Okay, so this is the definition of the gamma function. I've always wondered why, at least when I first saw it, why x to the s minus 1? Why not put x to the s? In which case you will actually get factorials. Here you will get gamma of n is n minus 1 factorial. And the reason is this is connected with the Mellin transform more naturally to put the x minus 1 to the Laplace Mellin transform. So it comes from there. But this one is, as an integral, convergent only when real part s is greater than 0. Because at the 0 end, the 1 over x will diverge. But 1 over square root of x, even though it's infinite in size, the integral dx over square root of x is still convergent, or dx over x to the 2/3 is still convergent. X to the 1 minus delta is still convergent, but not x to the minus 1. So I need real part s greater than 0 for this integral to converge. And this is an analytic function in that half plane. Right? So now what we do is, let's integrate by parts, okay? So integrating by parts, we get still in real part s positive, we get gamma s is equal to, I now integrate this by parts, so I integrate the x to the s minus 1, so I get e to the minus x to the s divided by s between 0 and infinity, and then minus of the integral from 0 to infinity 1 over s, and then I have x to the s, and now the derivative of e to the minus x will give me e to the minus x dx. Now this integral vanishes at the infinity end due to the e to the minus x, and now the real part s greater than 0 comes into play, and therefore this is a positive power of x, so it vanishes at x equal to 0. So this evaluation is 0, so this is equal to 1 over s times the integral from 0 to infinity e to the minus x to the power of x dx, and that is clearly 1 over s gamma of s plus 1. So it leads to the functional equation, leading to the functional equation gamma of s plus 1 is s gamma s. This 1 and this is 2. All right, so if we now iterate this, okay, so by iteration, an evaluation, of course, of gamma of 1, we get gamma of n is n minus 1 factorial for n equal to 1, 2, etc. Okay, so n equal to 1 is 0 factorial. You just evaluate that at s equal to 1 or n equal to 1, right? And so you just get e to the minus x, that's 1, and then the next one will be still 1, and then 2, and then so on. So gamma of n turns out to be n minus 1 factorial. All right, but now, because I have a functional equation, and I have the definition of the gamma function here by integral, I can use the value of the gamma function here to get the value of the gamma function 1 unit to the left. So from here to here. So if this is known, then I know this. I'll plug it in. If that's known, then I know from this functional equation s minus 1. So this functional equation permits you to extend the gamma function to the entire complex plane as a meromorphic function. Okay, so from the functional equation, we extend gamma of S to be a meromorphic function in all of C. And when you do that, the problem arises only by division by S, right? So gamma S is gamma S plus 1 divided by S. So the first problem occurs at S equal to 0. But if there is a problem at S equal to 0, that problem will continue to show at S equal to minus 1. And will continue to show at S equal to minus 2. But nowhere else will this functional equation ever cause a problem. So the poles of the gamma function will be at the non-negative, the non-positive integers, okay, into all of C with poles, or with singularities, I would first say, only at S equal to 0, minus 1, minus 2, and so on. And these are all simple poles. So the gamma function has simple poles at the non-positive integers. Now what about zeros? It's very interesting that the gamma function has actually no zeros in the complex plane. And that comes from a product representation for the gamma function. So in fact, another topic, so I'm going to maybe list a few topics, and I'm going to request or encourage some of you to give talks. So one talk would be on the gamma function. Another talk is on generalized Dirichlet series from Bohr's thesis, and I will give you a couple of more topics. So it's nice to pick up. So these are all simple poles. So this is an important fact. Is gamma S is zero free in, so that means 1 over gamma S is an entire function. So it's absolutely zero free, so it's actually an entire function. So you can expand 1 over gamma S from here, the radius of convergence will be infinity. So special values of the gamma function are of interest to us. So let us compute one value which is going to be used now. So let us look at what is gamma half. Okay, so gamma half is, by definition, integral 0 to infinity e to the minus x, x to the minus half dx. That's gamma s. So now put x equal to u squared. So then you have dx is 2u du. So this is equal to integral from 0 to infinity e to the minus u squared. X to the minus half is 1 over u. And then dx is 2u du. And therefore, this is 2 times this integral, which is the integral from minus infinity to plus infinity, e to the minus u squared du. That, of course, is the Gaussian integral to the square root of pi. So gamma half equals the square root of pi is a value that we are going to be using in our estimations of the Riemann zeta function. By the way, so gamma half is transcendental. Now, what other values do we know? What is the first? So Chudnovsky, this Russian mathematician, became world famous when he showed that gamma 1/4 is transcendental. So that was his ticket to fame, because he proved many other important things later. But that was one of the first things that he did. So special values of the gamma function are of great interest. Sometimes you may not know the value, but you want to still establish that it is transcendental. So gamma 1/4 is transcendental, which is famous. Okay, so that's about the gamma 1/2. So now let us move on to the functional equation for the zeta function. So this is Riemann's theorem. So the theorem is the function zeta s is analytic all of C except for a simple pole at s equal to 1 with residue 1 and satisfies the function equation here's the function equation, pi to the minus 1/2 s, gamma 1/2 s, zeta of s is pi to the minus 1 minus s over 2, gamma 1 minus s over 2, zeta 1 minus s. So this product is symmetric, is invariant as s goes to 1 minus s. Okay, so that's what this is. So let me draw a picture here. What is s goes to 1 minus s? S goes to 1 minus s is a reflection around the point half. Because s equal to 1 minus s is 1/2. So if I have s here, I do that, and then I extend by the same distance. So that's 1 minus s. So s goes to 1 minus s is this reflection. And so this is where the Riemann hypothesis is being motivated. So if you look at this line with real part half, that's sigma equal to half. I've got a problem with my thumb because I'm not able to hold the chart to it. So s goes to 1 minus s is basically this complex conjugation. So it's not giving you new zeros, right? So every zero here would be a zero there. But that's also obvious because the Riemann zeta function is a function with which is real valued on the real axis. And consequently, any power series expansion, let's say around 0 or whatever, is going to have real coefficients. Because if it's real valued on the real axis, all its derivatives must be positive, or must be real valued. So it'll have real coefficients. And if you have real coefficients, then f of z bar will be f of z bar. So this is a 0, then this is automatically a 0. But it's also indicated by s goes to 1 minus s. So but Riemann said because of this reflection symmetry, that all the zeros of the Riemann zeta function will lie here except so-called trivial zeros, which would be at -2, -4, -6, and so on. And that is really coming from the poles of the gamma function, dilated by 2, s over 2. So we'll see that as we finish after we complete the proof. Okay, so let's prove this. So now I'm going to define a slight variant of the theta function that we saw. So theta of t. So this is a different style of theta. So this is summation n from k from 1 to infinity e to the minus pi k squared t. And this is for real part t positive. So this is exactly what we had before, except that now the series is from 1 to infinity. Okay, so that's what I have. So I'm going to call this 3. So, so just note that the theta function that I had before, which is the double sum, is 2 times this theta function because of the reflection symmetry plus 1. Okay, and therefore the functional equation, thus the transformation formula for this theta function is transformation formula is theta of t is 1 over 2 square root of t times 2 times theta of 1 over t plus 1 minus half. So this is the transformation formula for this theta function, right? So this 2 times theta of 1 over t plus 1 is precisely this theta function evaluated at 1 over t. So I bring this here, I get half, and then I multiply it by 2. I will get 2 times this theta plus 1, and that's this theta function. So we have the old function equation, and the old theta function is 1 over square root of t of theta of 1 over t. So it's the same thing. All right. So this is the transformation formula for this theta function. So now, at this, how does the gamma function come? That's a stroke of genius of Riemann to bring in the gamma function. Okay. So now we use the so from the representation of the gamma function. Gamma, we have gamma of S over 2. So this is the thing, why did Riemann think of S over 2? You will see in a moment. So gamma of S over 2 is the integral from 0 to infinity e to the minus x to the power S over 2 minus 1 dx. And this is in for sigma greater than 0, real part positive. Right, that's the integral representation. Now what we're going to do is this. In 5, replace x by pi n squared x for a given n. So consider n as an integer and do this for a given n. And you will see why in a moment. So what do we get? If I replace x by pi n squared x, you get gamma of S over 2 is still an integral from 0 to infinity. This x is minus pi n squared x. Your x to the S over 2 minus 1, when I replace that, is x to the S over 2 minus 1. Okay? Times pi to the power S over 2 minus 1. N squared to the power S over 2 minus 1, which is n to the power S minus 2. Right? And then multiplied by, the dx is now replaced by pi n squared dx. So you end up with pi to the S over 2 so you end up with pi to the S over 2 outside. Now I've got n to the S over 2 n squared. So I get n to the S outside. And then I have got, so this is accounted for, right? And then I have got e to the minus pi n squared x to the S over 2. That's what I have there. Which means I have 1 over n to the S, and I want Riemann's zeta function. So I get the 1 over n to the S outside is equal to pi to the S over 2 divided by gamma S over 2 times the integral from 0 to infinity e to the minus pi n squared x x to the S minus S over 2 minus 1 x. Okay. Now, what I want to do is to sum this expression n from 1 to infinity. However, I can't sum this expression unless the real part S is greater than 1, because the Riemann zeta function sum is defined only in S greater than 1. So even though the integral is defined in s greater than 0, when I start summing this integral over all n, I have to go to s greater than 1. Okay. If real part s is greater than 1, we can sum the expression on both sides of 6 over n greater than or equal to 1 to get what? So I end up getting zeta s is equal to I to the s over 2 over gamma s. And now this sum is my theta function. Now of course I have interchanged summation and integration.
You want gamma of s over 2?
S over 2, sorry. X. Dx. So that's what we get. So this new theta function is brought in, and then we have this, but this is for real s greater than 1. So what we are really going to do is, we are going to show the connection between s and 1 minus s using this. But then you will say, sir, we have a little bit of a problem, because when s is greater than 1, real s, 1 minus s is here. So there is a hole. So this is then one universe and this is another universe. That's where that simple thing we did early on, where we used the fractional part to extend the Riemann zeta function from real part s greater than 1 to real part s greater than 0, becomes useful because that extension has already given you the Riemann zeta function up to this point. So s to 1 minus s, if you take the closed line from here, will give you now the entire plane. So simple as that was, that is the crucial step in linking the whole. This is the critical strip between s goes to 1 minus s applied only to the real part s greater than. So we'll have to come back and use that other representation, because otherwise we cannot fill this gap. Okay, so that's where that small step is technically useful. Right, so this is what we get for real part s greater than 1. All right, so now we will rewrite this. Okay, rewrite 7 as zeta s is equal to integral 0 to 1 x to the power s over 2 minus 1 theta x dx plus integral 1 to infinity x to the power s over 2 minus 1 theta of x dx. Right now, still in real part s greater than 1. Otherwise I can't use zeta. Until I have established the functional equation, I can't use real part s less than 1 in this game. All right, so we have this. Now, we use the functional equation. The functional equation for this modified theta function connects the value of theta with the value at 1 over t. And now there's a small technicality you have to take into account. This t goes to 1 over t is a transformation which converts 0, 1 to 1 infinity. So we say, call this 8. Use the transformation formula in 4. To rewrite 8 as zeta of s is equal to the integral from 0 to infinity x to the power s over 2, okay, I'll write this down for you, s over 2 minus 1, I'll still have 0, 1, and I'll convert it. S over 2 minus 1 of 1 over square root of x, theta of 1 over x, just put that, plus 1 over 2 square root of x minus half. Okay? Dx. So that's just that. Plus the integral from 1 to infinity, of course. So we are now going to rewrite this as an integral from 1 to infinity, but in a moment, not yet. Now, these two integrals I can evaluate exactly. They are just a 0, 1 integral of a power. So this integral is x to the power s over 2 minus 1, minus 3 halves. Now s over 2 minus 3 halves is still well defined because the real part of s is greater than 1 now. So the real part of s over 2 is greater than half. So s over 2 minus 3 half, the real part is still greater than minus 1. It's only at minus 1 that the integral diverges. See, e to the power, if I had x to the minus 1, that will diverge at the set, that will give you log. But not if it is x to the power 1 minus delta. It will not diverge. So I'm safe here. Okay. Therefore, these two integrals can be evaluated. So we can write this as equal to. So let us first write this as integral from 0 to 1, x to the s over 2 minus 1, not minus 1, minus 3 halves. Theta of x dx plus 1/2 integral 0 to 1 x to the power s over 2 minus 3 halves dx coming from this minus 1/2 the integral from 0 to 1 x to the power s over 2 minus 1 dx. Now these integrals, of course, can be evaluated exactly. Right? This integral is what? It is, all right, so s to the power 3 halves. So this integral will be exactly 1 over s minus 1 minus 1 over s because of the half. See, this one is antiderivative divided by s over 2. 2 and 2 cancel, will give you that. This is antiderivative, correct? I have to add a 1, so I get s over 2 minus half divided by s over 2 minus half, and then I get that. So you get 1 over s minus 1 minus 1 over s from the first part. And then I have got this integral, 0 to 1, x to the power s over 2 minus 3 halves theta of x dx, which I will now write as 1 over s times s minus 1 plus integral 0 to 1 x to the s over 2 minus 3 halves theta x dx. Now, I will rewrite this integral. Did I make a mistake? Yes, I did. That's all. Now, if I put 1 over x equal to u in this one, okay, so this is 10. Right. Now, put 1 over x equal to u in the integral in 10. To get what? the integral 0 to 1, x to the s over 2 minus 3 halves theta of 1 over x dx is integral from 0 to from 1 to infinity. Your dx is, so x is 1 over u, so dx is minus 1 over u squared, right? So I've got a plus sign, so it changes, reverse of the integral. So I get theta u, but now this is going to be x to the power, I'm just going to write it and check my calculation, u to the power at du. Is that correct? So that is u to the minus half, but then I have got a u squared, and that is a u to the 3 halves, there is a u squared at the bottom, so I get u to the minus half. Okay. This yields what? Theta of s is 1 over s times s minus 1, and now I'm going to add this 1 infinity integral with this 1 infinity integral. And so I'm going to get plus the integral from 1 to infinity of, I'm just going to call it theta x, then I'm going to have x to the s over 2 minus 1, and then I'm going to have x to the minus s over 2 minus half dx. But now you see, you don't have to be nervous with the minus, because this is in real part s, this is now from 1 to infinity. We no longer have the singularity at x equal to 0 to deal with. So this we have. Okay, so this will be given. All right, so now this integral I'm going to call as h of s. Okay, so that's your definition of h. Now, what can we say about h of s? So here's an important observation about h of s. Observe that h of s is h of 1 minus s. Because if I replace s by 1 minus s, I will get minus s over 2. I have half minus 1, and that's minus half. If I replace s by 1 minus s here, I will get plus s over 2. Then I will get another minus half, and I will get minus half with minus 1. So s goes to 1 minus s, converts this to this, and that to that. So the theta remains invariant. So this object is satisfies the equation h of s equal to h of 1 minus s. But also something else we can say. What do we know about this theta function? This